We tend to think of coastlines as these fixed lines on a map, right? But the truth is, they're some of the most dynamic, ever-changing places on the entire planet. They're constantly being sculpted by a sort of invisible architect. In this explainer, we're going to pull back the curtain on the powerful forces that build and then rebuild our shores every single day. So, have you ever gone back to your favorite beach, maybe after a few months or a year, and noticed it looks different? Maybe it's a little wider or narrower, or the sand has just shifted around. Well, I'm here to tell you it is not your imagination. It's the result of this massive, nonstop construction project that's being run by nature itself. So, what's really the engine behind all this constant change? Okay, the best way to picture this is to imagine a giant, invisible conveyor belt running all along the edge of every continent. This conveyor belt is always on, constantly picking up sand and sediment in one spot and just dropping it off in another. It really is the primary engine of coastal change, and it has a very specific name. And that engine, it's called longshore drift. Now, the absolutely crucial part of this definition is that last little bit, waves hitting the shore at an angle. See, if waves came in perfectly straight, our beaches would be a lot more static. But because they almost always come in at some kind of angle, they create this fascinating, continuous dance of sediment. And here's that process in action, what I like to call the zigzag dance. So a wave comes in at an angle, and it pushes sand up the beach in that very same direction. We call that the swash. But then good old gravity takes over, and gravity doesn't care about angles. It just pulls everything straight back down toward the sea. That's the backwash. This constant angled push and straight pull creates this net zigzag movement. It's basically a slow but relentless river of sand flowing right along the coastline. But here's the thing. This coastal conveyor belt doesn't always run at the same speed. Nope. Its pace is actually controlled by a few key things. How much energy is packed into those waves? How often are they hitting the shore? I mean, a big winter storm is going to move way more material than a calm summer day. And, maybe most importantly, it all depends on what's available to move in the first place. A loose sandy beach is going to change a heck of a lot faster than a solid rocky shore. But longshore drift isn't working alone. It doesn't happen in a vacuum. It's just one piece of a much bigger, more complex system. So let's move on and take a look at how other powerful forces, like the tides, come in and modify the work of our coastal conveyor belt. Think about it this way. The tide, that daily rise and fall of the sea level, it basically decides how big the workspace is for the waves. If you have a really big tidal range, you're giving the waves a huge canvas to work on, letting them move sediment over a much, much wider area of the beach. And this contrast is so important. During what we call spring tides, that's when the sun and moon's gravity are aligned, we get the highest high tides and the lowest low tides. This means waves can reach way up high on the beach and pull sand from there and then deposit it far out. But during neap tides, the range is much smaller. The wave's impact is a lot more confined, and way less material gets moved around. And just when you think you've got it figured out, there's more. It's not only waves and tides. You've also got nearshore currents, which are driven by wind and even the Earth's rotation. They just add another whole layer of complexity to the mix. They interact with everything else to create these incredibly intricate patterns of sediment movement, especially in places like estuaries and inlets. Okay, so we've got all these different forces pulling and pushing. How on earth do scientists even begin to make sense of it all? Well, they do it by zooming out. They look at the coast not as one infinite line, but as a series of distinct kind of self-contained systems. This brings us to the coast's big balancing act. And the key concept here is something called the sediment cell. Just think of it like a self-contained coastal neighborhood. All the sand and shingle in this neighborhood, well, they're born there, they move around within its boundaries, and they eventually get deposited there. Very little of that sediment ever crosses the property line into the next cell over. So every single one of these cells has three basic parts. You've got these sources, which is where all the sediment comes from. Think of cliffs eroding away or rivers carrying silt down to the sea. Then you have the transfers, which is the movement part of the system, and our friend longshore drift is the absolute star player here. And finally, you have these sinks. These are the deposition zones where the sediment eventually comes to rest, building up features like beaches or big sandbars. And this brings us to this really crucial idea: dynamic equilibrium. See, a healthy coastline isn't static. It's not unchanging at all. It's in constant flux.
But in a balanced system, the amount of new material being added from the sources roughly equals what's being deposited in the sinks over time. The system is always moving, but it's in balance.
So, why does any of this matter? Well, understanding this natural balance is everything. Because what happens when we as humans start messing with that equilibrium? The real-world implications can be, well, immense. See, the thing about a sediment cell is that it's all deeply connected. An action in one place has consequences somewhere else. If you change one part of it, let's say you dam a river miles inland, or build just one single breakwater, you don't just affect that one spot. You send ripples, sometimes pretty devastating ones, all the way down the coast. And these are just some classic examples of those unintended consequences. You build a dam for power, and it traps all the sediment that would normally feed the coast. What happens? You end up starving the beaches downstream until they literally erode away. Or think about those wooden fences you see on beaches. They're called groins. They do their job, they trap sand, but it's a zero-sum game. The beach right next door is now deprived of that sand, and it starts to disappear. Every action has a reaction. But hey, we have to remember, this whole process isn't just about erosion and destruction. It's also an incredible construction project. All that moving sand builds these amazing natural features. Things like spits, which are like long fingers of sand stretching across bays, or offshore bars that create calm lagoons, and even entire barrier beaches that act as the first line of defense for the mainland. And that just leaves us with this huge, kind of mind-bending question, right? We spend billions of dollars trying to preserve our coastlines, to hold them perfectly in place. But if the very nature of a healthy coast is this dynamic equilibrium, this constant balanced change, what exactly are we trying to hold on to? It's a thought that completely reframes how we should be thinking about living by the sea.